Hello everyone, I'm Tomohiro Oishi, now working in the Yukawa Institute for Theoretical Physics in Kyoto University. The title of my talk today is Nuclear Spin-isospin Excitations within the Relativistic Energy Density Functional Framework. My collaborators include Professor Niels Bahr, Ante Ravlitz, and Goran Krucic. So let me first introduce the target of my research now, that is spin-isospin mode. And the first category in the spin-isospin mode is isovector magnetic dipole. And here I wrote the isovector M1 operator. This operator contains the spin-isospin excitation operator, that is this tau and S. Then its selection rule reads from the even ground state nuclei, that is 0 plus to 1 plus states. And in M1 transitions, main contributions stem from the spin orbit splittings as well as the relevant residual interactions. Here, I wrote the reduced matrix elements of the operator S. Then, from this delta L-L, one can read that only the J upper to J lower or the J lower to the J upper transition is allowed. And also, the M1 transition plays a role in the determination of neutron capture rates of significance for the R process nucleosynthesis. The second category of spin-isospin mode is Gamow-Teller transition. The Gamow-Teller transition is the main component of charge exchange reactions and beta radioactivity, and here its operator is similar to the M1, and the selection rule is the same, but including the charge exchanging invoked by these tau plus minus operators. To determine the strength of Gamow-Teller, that is this BGT, two experimental probes have been utilized. The first one is weak interaction probe, that is nothing but beta radioactivity. Then the second is the strong interaction probe, that is charge exchanging reactions, for example by protons or helium-3 scattering. Then the Gamow-Teller transitions is closely connected with the nucleosynthesis, neutrino-induced reactions, and double beta decays. Okay, let's compare the M1 and Gamow-Teller transitions. Here in the left-hand side of this screen, I show one example of calcium-42 nucleus. From this nucleus, by this M1 transition, the two neutrons in the F7½ orbit are excited to the F5½ orbit. On the other side, by this Gamow-Teller transition, two neutrons in the same orbit are transformed to the protons in F7½ orbit or F5½ orbit. So the excitation energy of M1 can be approximated as the spin-orbit splitting gap between neutrons F5½ and F7½ orbits. On the other side, the gap between two Gamow-Teller transition peaks should be approximated as the spin-orbit splitting gap of the same levels but in the proton side. So, the M1 and Gamow-Teller transitions can be interpreted as the isobaric analog transitions. And one natural question rises: does the theory reproduces them simultaneously? Namely, does our theory reproduces these experimental data by correctly considering their spin-orbit splitting gaps as well as the relevant residual interactions? That was the original question I started this project. To answer to that question, in this study I utilized these tools, namely, the basic idea of my approach is relativistic energy density functional theory. Then I implement the mean field calculation of the relativistic Hartree-Bogoliubov type utilizing the DDPC1 setting. Actually, this is the one set of parameters to determine the energy density function. To calculate the magnetic dipole and Gamow-Teller transitions, I also utilize the relativistic quasi-particle random phase approximation calculations. Then, in these calculations, I consider the effect of isovector pseudovector residual interaction as well as pairing interaction. The nuclear energy density functional theory has been utilized as one tool to calculate the nuclear properties widely in the nuclear chart. There are two categories, that is, non-relativistic and relativistic EDFs. The former one includes scar, Goni, etc., whereas the later option includes meson exchange or point coupling models. For their implementations, to calculate the ground states, the self-consistent EDF mean field calculation has been utilized. On the other side, to calculate their dynamical properties like collective excitations, the quasi-particle random phase approximation, as well as, more generally, time-dependent EDF frameworks has been utilized. Here, I show one example of QRPA that is indeed a powerful tool to calculate this kind of photoabsorption cross-section. What relativistic density functional theory provides? Actually, I utilize the relativistic version of EDF for nuclear many-body problems, and that is determined, for example, by this Lagrangian. And actually, there are several motivations and cautions to choose the relativistic EDF framework. The first one is, in the original work by J.D. Wallecker, his original motivation was to obtain the stress tensor for Einstein equation of neutron stars. This purpose needs the relativistic formalism. As a successful result by Wallecker, the repulsive core of the nuclear force in the high-density region can be naturally concluded. The second, the Dirac-Lorentz formalism leads to a consistent treatment of spin degrees of freedom as well as a unified description of time-even and time-odd fields. Also, the relativistic effect and causality can be included. Third, connection between the force and meson is clear, for example, tensor forces from one pion exchange. Then finally, as a caution, spin orbital level splitting, which is one fundamental feature of atomic nuclei, is naturally concluded. This character is linked to the magnetic dipole and Gamow-Teller excitations, which are main topics now. This panel shows how the spin orbit splitting is derived from the Dirac equation. The Dirac equation including the scalar and vector potentials coming from the scalar and vector mesons. Then, by transforming this original equation, this kind of Schrödinger-like format, one can naturally find the spin orbit level splitting. Now, let's return to the original question, that is, does the theory reproduces the magnetic dipole and Gamow-Teller transitions simultaneously? And actually, this question sounds more critical for relativistic energy density functional theory, because that theory utilizes the relativistic formalism, which naturally concludes the spin orbit splitting. But if their spin orbit level splitting is not correct, it must mean that that theory is meaningless to explain the nuclear many-body problems. So, the magnetic dipole and Gamow-Teller transitions can be a good subject for our EDF theory to check whether the theory is really useful or not. And in this presentation, I utilize the point coupling version of our EDF Lagrangian, and that is formulated by this and including these interaction terms. And this interaction term includes isoscalar-scalar point coupling as well as isoscalar vector, isovector vector, blah blah blah. Totally these interaction terms. Now let me summarize my method. I utilize the point coupling REDF Lagrangian, which includes the isoscalar-scalar, isoscalar vector, isovector vector, and isovector pseudovector couplings. For the ground state of even nuclei, the relativistic Hartree-Bogoliubov calculation is performed by using this DDPC1 Lagrangian. On the other side, this isovector pseudovector Lagrangian is not active for 0+ ground states because of the selection rule. Then, Goni D1S pairing is also used for the particle-particle channel in open shell nuclei. For the M1 GT excited states, the relativistic QRPA is also employed. In the M1 GT QRPA, we additionally consider this residual Lagrangian coupling as, that is the residual interaction, and note that this isovector pseudovector coupling originates in the 1-pion exchange. Alright, so let me show the results of our calculations. The first result is non-perturbed calculations. Here, the non-perturbed calculation means that, I only use the DDPC1 Lagrangian, whereas the isovector pseudovector and pairing interactions are all neglected. Then I calculate the M1 and GT response functions as these by utilizing these two kinds of operators. So the central figure shows our result of non-perturbed calculations, and in this case we focus on these three nuclei, that is oxygen 18, calcium 42, and calcium 48. In the M1 side, there is only single peak. On the other side, in the GT excitation side, there are two peaks. And let me explain that the single peak of M1 is from this neutron 1d or neutron F7 in calcium isotopes to the neutron F5 orbit. On the other side, in the Gamow-Teller transitions, the higher energy peak is actually the equivalent product of M1, but including the charge exchange, like, for example, in calcium isotopes, this higher energy higher energy Gamow-Teller is from neutrons F7 to proton F5 orbit transitions. On the other side, in the GT excitation strengths, there is another low-lying strength. And actually, this means that the transition from neutron to proton, keeping the same angular momentum level, but only including the charge exchange. And here, by seeing this figure, first, the M1 and higher energy Gamow-Teller strength is mostly equivalent, namely, equivalence between M1 and higher GT is confirmed. Then also, GT minus has another low-lying response. And we also check that Ikeda-Fujita sum rule for Gamow-Teller is validated, as well as Curtis sum rule for M1 excitation is also validated. Next step is the full QRPA with residual interactions. And here, residual interactions include the isovector pseudovector Lagrangian in the particle Hall channel of QRPA, and also the pairings for open shell nuclei. And here we utilize two kinds of pairings, that is isospin singlet pairing for proton-neutron and isospin triplet pairing for proton-proton and neutron-neutron pairs. Full-REDF-QRPA results. Here I focus on the doubly magic nuclei, and those are this calcium 48 and these lead 208. Then, because of the doubly shell closure, their pairing interactions are not active. So, the residual interaction contains only this isovector pseudovector coupling in this case. In this left-hand side figure, I show some results by changing or by enhancing the coupling constant of this isovector pseudovector Lagrangian. By increasing its coupling constant, one can figure out that their excitation energies are shifted to the higher energy side, both in M1 and GT, like from this figure, peak to this peak, or this peak to this peak. Then, in this central figure, I show the corresponding results, that is the calculated excitation energies by Gamow-Teller and M1 operators. Again, by increasing this coupling constant, their excitation energies are increased. So that is the common feature both in M1 and GT cases. But okay, let's return to this left-hand side figure, and let's remember that in this non-perturbed case with the zero of alpha IBPV, then the strength function of M1 and GT are mostly equivalent. That means that isobaric analog symmetry is well kept when the isovector pseudovector residual interaction is neglected. That is also true in lead-2weight, like this two-peak structure is really similar to this two-peak structure in the GT- side. But by enhancing the isovector pseudovector coupling constant, then the M1 peak is reduced, whereas the corresponding higher energy GT- strength is enhanced. So that is an opposite behavior, namely, as the residual isovector pseudovector interaction becomes stronger, the M1 and GT modes becomes more divergent from each other. Namely, the isovector pseudovector interaction disrupts the isobaric analog symmetry between M1 and GT. And at the second point, let me also explain that the simultaneous reproduction of M1 and GT energies for both light and heavy nuclei is still demanding. And what does it mean? Actually, okay, in this left-hand side figure, I fit this coupling constant to this low-lying GT- energy in this case. But even though I fit this parameter to this energy, for the other experimental data of M1 and GT- energies in lead-208 and calcium-48, unfortunately, that is still not good. Namely, using only this single parameter is, or maybe not enough to simultaneously reproduce all these experimental data. And that is the problem for future study. Mirror symmetry of M1 and GT transitions. Next, let's move to the calcium-42 and titan-42 nuclei. And actually, they are so-called mirror symmetric partners in the nuclear chart, as shown here. Then we calculate their M1 and GT- strength functions by using the REDF-QRPA. So both in M1 and GT- or GT+ cases, their transitions show an agreement between mirror symmetric nuclei. So that means that mirror symmetry in M1 and the same symmetry in GT ± transitions are well confirmed. Role of proton-neutron pairing. For these calcium-42 and titanium-42 nuclei, because they are open shell, we took the pairing interactions into account, especially to reproduce this low-lying Gamow-Teller excitation energy, that is this 0.611 MeV in this experimental data. Actually, the proton-neutron pairing plays an essential role. If we did not take this proton-neutron pairing into account, okay, the excitation energy shows up at really higher than the experimental data. So to adjust our parameters in the REDF calculations, okay, especially the proton-neutron pairing is a key of this problem. Finally, I mentioned the absence of higher energy Gamow-Teller strengths. Okay, for this calcium-42 nucleus, from these calculated strength functions, in this figure, I also show the cumulative summation of strengths, that is the integration up to certain energy of these strength functions. So, and here, this dotted line is the Ikeda-Fujita sum rule value, that is the model-independent sum rule determined from the calculated Gamow-Teller minus and Gamow-Teller strengths. So, And here the experimental data is at only of 0.6 on the other side. Our low-lying GT minus strength is in a good agreement with this experimental data. So that means that up to this, let's say, their first energy peak, the good agreement between calculations and experiments is confirmed. But in the higher energy region, our calculations predict their second peak, several another peaks, but those peaks are not confirmed in this experimental data. So the giant Gamow-Teller transitions somehow vanish in the experiments. As one possible reason, now we are discussing the effect of continuum states. Summary of my talk. The relativistic Hartree-Bogoliubov plus QRPA computation is applied to the magnetic dipole and Gamow-Teller excitations. It is shown that the isovector pseudovector coupling remarkably affects their excitation properties. For simultaneous reproduction of M1 and GT of various nuclei, we need to improve the REDF Lagrangian, for example, with the density-dependent isovector pseudovector coupling to produce their excitation energies. Then the pairing interactions provide a sizable effect on these spin-isospin transitions, especially the proton-neutron pairing is important to explain the low-lying GT excitations. For future works, improvement of the REDF parameters are in progress now. The experimental data on the M1 and GT may be a suitable reference for our study. For neutron-rich and proton-rich nuclei, we also need to take the deformations into account. Also, the collaborations with quantum computing and AI technologies for REDF calculations are considered. Thank you for your attention.